The emergency pediatrics healthcare field is always at the forefront of engineering innovation. To this day, it can be difficult to secure a pediatric ventilator mask on young patients without applying excessive pressure upon their skin. This imperfect fit can lead to irritation of the skin and reduced blood flow at the points of excessive acute force. Currently, the only feedback readily available to healthcare workers is an oxygen leakage percentage of the mask. The goal of this design project is to prevent skin injury in young patients by incorporating proximity sensing capabilities in a non-invasive ventilator mask to help determine appropriate fit. Two main methods were developed and implemented toward this end, one rigid and one flexible. Both methods are then connected to a data acquisition system designed by the team to provide feedback for the healthcare workers in the form of an LED output to improve the fitting process. The rigid approach is based upon sensors built into a printed circuit board, or PCB. The PCB was designed to support the shielding of the sensors from the external interference and houses the supporting hardware on the top layer of the board. A custom 3D printed frame was designed to secure the PCB over the surface of the skin. The flexible solution is based upon silver ink sensors attached directly to the surface of a ventilator mask. The sensors were fabricated using an aerosol jet printer at the Cleveland State University Printing Lab by Tyler Holdsworth and Dr. Lily Dong. The sensors were then attached to the mask and electrically connected through a combination of epoxy and Kapton tape. To facilitate more accurate testing of both approaches, the team designed a precision rail system with 0.03 millimeters of accuracy. The system operates by driving a conductive material toward and away from the sensor under test. Both rigid and flexible approaches are connected to an LED output system meant to assist the respiratory therapist with fitting the mask to the patient. The team wrote code to support the system, which causes the LEDs to gradually change from green to yellow to red as the mask presses more firmly against the skin, effectively using millimeter level displacements of the mask as a proxy for pressure. The location of each LED on the visual output system corresponds to the location of a sensor on the mask. The current range of sensing is between 0 and 0.5 millimeters for the flexible setup, and between 0 and 3 millimeters for the rigid solution. Here you can see both systems in action. Overall, the design and implementation of both methods has been successful. Additional improvements to the code could refine the information provided on the output based on the desire of the hospital workers. Due to the pandemic, the team was unable to perform testing and tuning of the system for a hospital environment. Future iterations of this project could custom tailor the sensing capabilities based on testing in a medical environment.